Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to go back and look at the concept of maximums and minimums on functions. And this time, we're going to see if it's possible to calculate them without having to look at the graph. So just a reminder of the vocabulary here. When we talk about extrema, we're talking about maximums and minimums. And these are broken up into two general categories, absolute and local. So the absolute would be the greatest, either maximum or the greatest minimum. So the biggest or smallest value in the function over the entire domain. And then when we talk about the local, we basically break it up into open intervals, and then we look in that region to see, is there a maximum or a minimum? Generally, when we're looking at a function, we look for where the function changes direction for that maximum and minimum. Because we're on the open interval, we don't look at those endpoints. So if we look at the little graph we have down here, for example, we have an absolute minimum. It would be this bottom curve. But we don't have an absolute maximum because it goes off to infinity on the endpoints. We do have a local maximum. It would be right here. And this is the only local maximum because anywhere else we look, if we were to try to draw an open interval, our graph continues off of that open interval. And then we have two local minimums. So the absolute minimum also happens to be a local minimum, and then of course we have this local minimum. Now, algebraically, what we typically do is we would just simply draw the lines across here, and you could easily check by using your horizontal line test to see whether or not it's an absolute or a local. Okay. However, in calculus, we have a different way of both finding these and testing these. So we have a theorem called Fermat's theorem that tells us that if a function has a local maximum or minimum and it's differentiable at that point, that the derivative at that point will be zero. And this is actually fully in line with what we know from our conceptual idea. So, for example, this graph is from a ball drop experiment that you might do in your physics class or calculus class. You take a ball, you have an infrared camera above it, and you drop the ball, and it measures the height of the ball over time. So the ball falls, hits the ground, and immediately bounces back up again. And it's affected by gravity, just like in Galileo's experiments. So the ball falls, bounces, falls, and bounces, so on and so forth, losing energy over time. And then as the ball reaches the top and gravity overcomes the energy from the bounce, you'll get a point where the ball is neither rising nor falling. It's got a velocity of zero, so the derivative would be zero at that point, which is fully in line with Fermat's theorem. Now, the problem is we have another spot where we have a local minimum, and Fermat's theorem doesn't really give us any way to examine that point, or any way to predict that there might be something at that point. And that's each of these little spikes. Because you'll notice one of the limitations of Fermat's theorem is that the function has to be differentiable at that point to even be into consideration. So our modern version of this expands this into an idea we call critical points. And we're going to look at that next. So in expanding Fermat's theorem, what we say is that these critical points are points on the domain where the derivative is either equal to zero or does not exist. Now, an important feature of this, though, is that when we look for these points, they cannot be the boundaries of that domain. So this kind of kicks out the concept of the piecewise function with the discontinuities. So if you remember, we had the three situations in which we would have the does not exist situation for continuous functions where they would not be differentiable. And those three situations were either the vertical situation, the kind of kink in the graph, or the discontinuity. So by saying that C has to be an internal point and not a boundary point, that kicks out that discontinuity situation. And so what this is really telling us is that we can look around on the graph without having to look at the graph. we can take the derivative of the function and then look at that derivative and know that the only places we need to examine on that function are where the derivative is equal to 0 or where the derivative doesn't exist, because that's going to be the places in the function where some kind of change happens. Because if you notice, look at our graphs. It's either where we're going from increasing to decreasing, or we're making a sudden change, or where we're going from concave down to concave up, or concave up to concave down. And we're going to examine this concept of concavity and saddle points more in a future video. But just know that we're going to be coming back to this idea of critical points and critical values when they're not maximums and minimums later. So let's go ahead and see how we can then further use this to actually not only look where we find a maximum or minimum, but also use this to find what those maximum and minimum would be. So putting everything together, we actually do come up with a way to try to find maximums and minimums without having to look at the graph. And the way we do that is probably exactly what you expect. We take the original function, we take the derivative, then we examine that derivative to try to find all of the places on an interval where it would be equal to 0 or where the derivative would not exist. Then we take those values and plug them into the original function and compare all of those values, as well as, on the closed interval, the endpoints. Whatever the highest values are going to be the absolute maximum on that closed interval, and whatever the lowest values are going to be the absolute minimums on that closed interval. And the reason we do this on a closed interval is because typically this is a practical application, because when we're looking at practical things, we usually have some kind of limitation, because things don't go on forever. Take that bouncing ball example. We have a starting point where we dropped the ball, and then eventually the ball will stop bouncing. So we have these practical limitations, even if mathematically we could say go on forever with our functions. And then the other reason we do this on a closed interval is because when we're looking for a local maximum or a local minimum, we can easily say whether or not that local maximum or local minimum exists by whether or not the absolute maximum or minimum is at the endpoint or one of the interior points. Because if the absolute maximum on that closed interval is an endpoint, that means that closed interval does not contain a local maximum or minimum for the function that that closed interval is part of. Let's look at a couple of examples. So go ahead and give these a try, and we'll go over the answers in 3, 2, 1. How'd you do? So on our first one here, nice and easy, we just take the derivative and then we factor out the t. Look at the discriminant here, and you find that we've got a 0 here for this t, and then there are no real zeros here, so we only have the one critical point. Over here, when we do our derivative, we get 4 minus the secant squared, so that means we need to be looking at this cosine squared. From our unit circle, we know that this is going to be undefined whenever the cosine squared is 0, so that's going to be at pi over 2, 90 degrees. And then we know that it's going to be equal to 1/2 whenever we're looking at pi over 3, 60 degrees. So every time we're on that circle at 60 degrees, we're going to be getting that 1/2 squared is going to be 1/4, flip it, and that's going to be 4. So that's where we're going to get our 0. And so when we're trying to write this out, it gets a little bit difficult here, because that means that we're going to be looking at pi over 2, and then every time we go around the circle, so every time we add 2 pi to that. And then for the 60 degrees, we're going to be looking at pi over 3, and then 2 pi over 3, and then 4 pi over 3, and then we go 5 pi over 3, and then we jump to 7 pi over 3, and then 8 pi over 3, and so on and so forth. So it gets a little bit difficult there. Feel free to use your technology to look at those ones, especially when we're looking at kind of unbounded trigonometric functions, because that periodicity of it will make it a little difficult. Okay? Now, when we're looking at these nice absolute ones, these ones are good because we have a nice closed domain that we're looking at. So here we again take our derivative and then we look for our critical values. We had a nice linear function, super simple. We get 3 points to check. We just plug the values back into the original function. Remember, we're checking the original function, not the derivative. We only use the derivative to find the critical values, and then we check the endpoints and the critical value, and we found that our maximum was 216, our minimum was 57. We do the same thing here for the trigonometric function. It might be a little harder when you're looking at the derivative there, but again, if you're used to using your unit circle, or if not, do the examination with your technology. Although, do be careful. They love to use radians. Get used to using your radians here. Although I did go ahead and use the approximation just for the comparison purposes here. And you find that we got our maximum at pi over 6 and then 3 root 3 over 2. And then our minimum was pi over 2 and 0. So I'm going to give you a couple of exercises to try on your own. And as usual, we'll put the answers at the end of the outro. So I hope this review of maximums, minimums, and then the look at Fermat's theorem as well as critical values was helpful. If you have any questions, remember you can drop into the comments or join us on Discord. And then the answers to the exercises will be at the end of the outro.